The advancement of additive manufacturing techniques in the last 15 years allowed the production of complex structures such as metal lattice structures using newer and newer alloys. However, in order to include these metamaterials in load-bearing applications, it is very important to evaluate their fatigue performances and the relation between the fatigue performances and the production technique. My name is Antonio Cutolo and I'm working as a PhD researcher at KU Leuven, a university in Belgium. In this presentation, I'm going to show the results of a study related to the fatigue performances of metal lattice structures produced via laser powder bed fusion using the A205 aluminum alloy. The A205 is a relatively new aluminum alloy with excellent mechanical properties. It is a lightweight with high strength and high thermal conductivity material. Therefore, it is quite suitable for aerospace and automotive industries to realize functional parts for load-bearing applications. In this study, the questions that we want to address are basically two. First of all, we want to understand if the material is suitable for production of metal lattice structures using laser powder bed fusion technique. And in a second stage, we want to understand if it is possible to predict the fatigue properties of these metal lattice structures. For these reasons, the content of the presentation will be organized in two parts. First of all, we are going to explore the parameter optimizations for sample production of the metal lattice structures that we use in this investigation. And in a second stage, we are going to explore the fatigue life prediction and the fatigue experimental campaigns that we conducted on the coupons. At the end, we are going to wrap up with some conclusions. The samples used in these investigations were produced on a 3D Systems Pro X 320 machine. They are composed by rhombic dodecahedron unit cells that were replicated to fill a volume of a cube of 14 millimeters of side. Rhombic dodecahedron unit cell is a bending-dominated unit cell that is composed by 32 struts connected by 8 nodes. We investigated 3 different relative densities, namely 10%, 20%, and 30% by changing the strut diameters from 200 microns for 10% relative densities up to 400 microns for 30%. The optimization process has been performed for 2 different relative densities, namely 10% and 30%. We started from the optimal parameter set for bulk coupons and we investigated the effect of the laser power and velocity on the metal lattice structure parts. Moreover, in order to produce lattice structures that are closer to the cut geometry, 2 scanning strategy parameters are investigated, namely the contour offset and the hatch offset. The main results of the parameter optimization process are presented in these pictures. On the left side, the first trials are presented. For these coupons, we used high laser power and velocity. The resulting quality is very poor, with severe dross formation affecting the outer surface of the struts. Moreover, looking at 30% coupons from a side, it is almost impossible to clearly distinguish a strut. On the right side, the coupons produced with the optimal parameter set are presented. In this case, the overall quality of the parts improved with a substantial reduction of the dross formation and of the molten particles on the strut surface. However, top view and side view show different strut thickness, indicating that the struts result slightly elongated along the building direction. The optimum parameter set presented in the table in the middle of this slide was used to produce 95 coupons with 3 different relative densities. After the production of, the coupons were removed from the base plate and cleaned using an ultrasonic bath. In the bottom table, the measured relative density are compared to the designed one. The RD10 specimens are very close to the design geometry, but these measurements start to deviate when going to higher relative densities. This is likely due to the large effect of the partially molten material particles on the RD10 structural relative density. The internal porosity of these structures is also investigated using both Archimedes and micro-CT analysis. And it can be noticed that for increasing design relative density, more and more defects are present in our structures. The CT scans allowed us to take a closer look to the defect populations generated during the manufacturing process. For RD10 coupons, it is possible to distinguish well-defined struts with very limited amount of internal residual porosity. These internal defects are very small and spherical, indicating that these pores consist of entrapped gas in the material. For RD30 coupons, there are clearly larger internal defects, both at the node locations and along the struts. These defects have low sphericity, meaning that they can be listed as lack of fusion pores. The presence of these defects can be explained considering the scanning strategies adopted for RD10 and RD30 coupons. For RD10 the scanning strategy consists only of one contour track. For RD30, the scanning strategy consists of a contour track followed by short infill tracks. These infill tracks are too short to result in a fully developed melt pool with the current parameter set, and so defects are generated. Micro-CT analysis was also performed to evaluate the differences between the produced coupons and the CAD geometries. The results presented in the pictures of this slide show good agreements between the produced part and the CAD, indicating high geometrical accuracy of the manufacturing process. The small differences captured by the micro-CT analysis can be attributed by the dross formation and to the unmolten particles attached to the external surface. Apart from the slight increase in internal porosity of RD30 coupons and these small geometrical deviations, we can conclude that we achieved our goal of building accurate, high-quality lattice structures with this aluminum alloy. Let's now move to the experimental campaign and the fatigue life prediction. The experimental campaign and fatigue life prediction consist of three phases. In the first phase, we carried experiments on the coupons with a relative density of 10%. The experiments were compression-compression fatigue tests with an R ratio of 10. In a second phase, we extract a local SN curve that we use to predict the fatigue performances of the RD20 and RD30 SN curves. In a third phase, we carried the same experiments on RD20 and RD30 coupons, trying to validate the predictions that we made in phase 2. Fatigue test results of phase 1 are presented in the graph on the left. 5 different stress levels were considered between 0.75 and 2.25 megapascal, with consequent fatigue lives varying from 10,000 to 4 million cycles. The graph on the right side shows local SN data that we extracted using the experimental results of phase 1. In order to clarify the concept of local SN curve, it is important to introduce the local stress method. When we look at fatigue performances of metal lattice structures, we can do it from two different points of view. The global point of view treats stresses as a ratio between the forces and the cross-section of the coupons. Given the same global stress, the more the material, the higher the fatigue resistance. Therefore, SN curves are strictly related to the coupon's relative density. But if we look locally, the external compressive stresses generate local bending and compression stresses along each strut. The strut, in this case, can be seen as clamp beams subjected to an inclined force that generate tensile and compressive stresses across the strut's cross-section. For fatigue problems, the local tensile stresses can be considered as the main driving factor for fatigue crack initiation. Considering the Gibson-Ashby relation between the strut diameter and the metal lattice structure relative density, it is possible to obtain a single SN curve that is not influenced by the relative density, but only by the material condition and by the surface condition of the coupons. This slide presents a schematic representation of how the local SN curve can be used as a predictive tool. In order to obtain the fatigue performances of the other two batches, RD20 and RD30, we use as an input the measured structural relative density to calculate the average strut's diameter using the Gibson and Ashby relation. Combining this information with the local SN curve, it is possible to calculate the force on each strut by reversing the local stress method formulation. Given the total number of nodes, it is finally possible to evaluate the total applied force in function of the number of cycles to failure and, consequently, the global SN curves for RD20 and RD30 coupons. The results of the prediction of the local stress approach are presented in the picture on the right side in terms of global stresses in function of the number of cycles to failure. 3 SN curves were obtained for the 3 different batches, showing higher fatigue resistance for higher relative density. Comparing the fatigue test results with the fatigue predictions, it is possible to appreciate how well the local stress approach can estimate the fatigue life of the metal lattice structures investigated in this study. This methodology could be extended to other metal lattice structures with different unit cells and produced with different materials to extract the structural fatigue life with a limited amount of coupons, saving time and money. To conclude this talk, it is possible to summarize the main findings of this study as it follows. A quasi-optimal parameter set for production of metal lattice structures with the A205 was obtained. Although this parameter set ensured high geometrical accuracy, improvements are still required to reduce the amount of internal defects that were generated for the coupons with higher relative densities. A methodology based on the local stress method has been proposed to fatigue the performances of the metal lattice structures. The procedure consists of one single set of SN data that is then converted into a local SN curve. This local SN curve has been successfully used to predict fatigue performances of the metal lattice structures investigated in the study. In fact, the comparison between the predictions and the experimental showed high correlation, highlighting the prediction capabilities of the local stress approach. With this slide, I would like to conclude my talk and thanks all the people that watched this video. Moreover, if there are questions, I would be happy to discuss them in the dedicated session.